Hi, this is the seventh live interactive session for the course Structural Geology offered by NPTEL. And this is week 7, and today's discussion is on foliation and lineation. So this is the course outline that we already talked about. So we have already covered 6 weeks, and this is the 7th week in which we will be solving problems related to foliations and lineation. And this is 7th September 2024. And this is the 7th live session of the course. And the time for course is live session is 4 p.m. to 6 p.m. And this is the session link to join the discussion forum. So, so about week 7's content. So in week 7, we mostly learned about the concept of planar and linear fabric in structural geology. Classification of planar fabrics, primarily primary and secondary foliations, type of primary foliations and their field identification, process of the formation of secondary foliation, geometric classification of secondary foliations, and then we talked about continuous and space foliation, including crenulation cleavages and their importance, and the importance of secondary foliation that we use in deciphering the regional deformation history, origin and classification of lineation, which are linear features, linear fabrics such as structural lineation, mineralogical lineation, penetrative and non-penetrative lineation, and also the use of linear features in understanding the regional deformation. So this was the summary of week 7, and based on these content, we will go ahead with our today's discussion where we will solving problems related to conceptual problems on planar and linear fabrics. And then we will summarize and conclude today's discussion session with a plan for upcoming live session that in that week, that means 8th week, in which we will be talking about fold and mechanism of folding. So just so let us start with today's problem solving session. So I have prepared some questions on planar and linear fabrics, and we will solve them. That will help you to understand how to deal with these kind of questions in assignments and also for many other kinds of competitive examinations that may appear. Okay, so the first question tells us that which of the following features may not be used to distinguish between a primary foliation and secondary foliation? And the options are given. Option A, reversal of sequence in an exposure. Option B, existence of symmetry planes in the exposure. Option C, compositional similarities between layers. And option D, along strike thickness variations in layers. So this question primarily tells us about the procedure of identifying whether a planar feature we are observing, whether that feature is a secondary foliation or is it a primary foliation. So primary foliation, if we just talk about primary foliations, they can come from two types of rocks which are sedimentary origin and another one is igneous origin. So mostly we see the primary foliations in field that are associated with deformation. They are in most of the cases associated with sedimentary rocks. That means we observe bedding planes, which are primary foliations, and associated sedimentary structures with those bedding planes. And we subsequently observe the deformation of the primary layers of the bedding planes, and then we interpret how the deformation has taken place and what are the variations in the regional deformation and so on. So, for sedimentary origin of primary foliations, we will mostly look for number one, sedimentary structures, which includes cross beddings, convolute structures, ripple marks, and other forms of seam sedimentary deformation structures. So these are the primary sedimentary structures that we observe. Now, if we have to follow the question that tells us that which may not be used to distinguish between a primary foliation and a secondary foliation. So reversal of a sequence in an exposure that is explicitly associated with the sequence of sediment deposition. And if we have to follow reversal of a sequence in an exposure, so if we have to detect whether the sequence is overturned or not, or it is reversed due to deformation, we have to look for these structures, right? Then we definitely have to go for observing either based on the fossil content of the rock, or by observing the uh, overturning of sedimentary structures. So just to go for the first option, we have to deal with these other criteria as well. So in that sense, we will be definitely identifying this sedimentary unit, right? So in that case, we may not be using the criteria to identify whether the sequence is reversed or not, right? So this is not correct in this case. So option A is not correct, because for to look reversal of a sequence, we will be dealing with this kind of identification, characteristic features of sedimentary rocks, and therefore we will be automatically identifying whether this unit is sedimentary or it is secondary foliation. Now, another point is the existence of symmetry planes in exposure. So, existence of symmetry plane are characteristic for secondary foliations, right? Why? Because secondary foliations generally appear symmetric and they are consistent. Say for example, I have developed, so this is, say for example, this is an asymmetric fold in the strata. We are observing this kind of asymmetric folding. So this will be the axial plane. So this axial plane will be mirroring the opposed part of this foliation, right? And if there exists a foliation plane along this orientation, I will identify many such planes in the same exposure of the same orientation. That means the secondary foliations will always be symmetric, right? So if I am particularly looking for a symmetry plane in the exposure, then I am of course identifying which one is the secondary foliation. So that doesn't make any sense. If I am not trying to go for a characteristic feature, then of course if I look for the existence of symmetry planes, I will be definitely identifying which one is the primary and which one is the secondary. Our question is that how can you not be doing that? So again, option B is not correct because it automatically identifies which one is the uh, symmetry plane. Now talking about option C, do you think that option C among all the four options is the correct, that it may not be the useful feature to distinguish between a primary foliation and secondary foliation? Because I can definitely say that option B, which is the along strike thickness variations in layers, along strike thickness variation of layers is a characteristic feature of primary bedding planes or bedding planes, right? So along strike variation will automatically tell us that which one of the following is a secondary foliation and which is a primary foliation. So now the option C remains, as that we will be looking for the compositional similarities between layers. So you see, this is a contradictory statement because for identifying primary foliation, we mostly go for the first observation is whether there is an existence of sedimentary structures, and then we look for the compositional contrast between layers. We see bandings, alternate dark and light color bandings. We observe that, and from that lithological contrast, we determine that okay, so this is a primary foliation, and based on that, we also determine the secondary foliation. Now, if we look for compositional similarities, then we are purposely eliminating the fact that compositional similarity within a rock cannot help us in identifying the whether this foliation is primary or of secondary origin, right? Only compositional contrast is if available, then from the field exposure we can identify okay, so this is a primary layer, and then if it's not, then it is a secondary layer if axial planar cleavage and other things are also available in that case. So option C is correct in this sense that looking for compositional similarities will not be helpful for distinguishing between a primary foliation and secondary foliation. But rest of the other options are the characteristic features that we use frequently in the field to identify or distinguish between a primary foliation and the secondary foliation. Okay, so this was the first question. Now let us move on to the second question. It says that a pebbly conglomerate has undergone pure shear deformation under plane strain condition. How will the pebbles in that rock look like along XZ and YZ sections of the explosion? Option A, linear along YZ section and circular along XZ section. Option B, circular along YZ section and linear along XZ section. Option C, both linear along YZ and XZ section. Option D, both circular along YZ and XZ section. So these are the four options. I will let you think for a moment and then we can solve this question.
Sir, linear along YZ section and circular along XZ section.
Linear along YZ section and circular along XZ section. I'm sorry, Paman, but I think option B will be correct in this case. That is circular along YZ section and linear along XZ section. Why I am telling that? So suppose you have
linear along sigma 1, na?
No, linear will be along lambda 1. So now you are talking about, whenever we are talking about strain, pure shear, consider this as a strain ellipsoid, right? So you have to think in terms of strain ellipse, not the stress ellipse, right? So say for example, this is your rock. Let's say I'm erasing it. So say for example, this is your initial sample, which is a cube. Right? So this is your initial sample and you have your coordinate as x. No, it's so this is z, this is x, and this is y. So this is your frame of coordinate, and now you are saying that you have applied plane strain condition. So plane strain condition means you will observe the deformation only along the exit section. So this section, the deformation will be restricted along this section only. In plane strain condition, the deformation is restricted along the exit section. So now if I apply pure shear, that means I am compressing in this direction and extending along this direction. So what will happen? Keeping the y dimension same, it will stretch and shorten along x and z axis respectively. So this will deform like this. So my y dimension is fixed. So along x, it is extended, and along Z it is shortened, right? So if initially if I had a pebble like this, right? Now the pebble is spherical. Consider the pebble to be spherical in initial shape. So every surface xz, yz, and xy, in every section, you will see circular cross section of the pebbles on every surface. But now what is happening? I am restricting the deformation along the yz plane, and I am extending the ellipse in this direction, right? And I am shortening it along this direction. So what will happen? It will eventually turn into, so it will eventually turn like this. The pebble, it will become like this, flattened and stretched. But since I am restricting my deformation only to the xz plane, when I'm looking from this yz plane, I'm seeing a spherical dot-like feature. But whenever I'm looking from this direction, I am seeing that it has been stretched, and the trace of this pebble will appear as linear feature. So if I cut across the section like this after the deformation, so I will see stretched linear features along the xz plane, and I will see dots or circular sections along the yz plane. So this is how deformation is taking place, and because of that deformation, which is pure shear and under plane strain condition, the main section that we observe, that is the xz section, because x is along lambda 1. So if I just plot the lambda 1, lambda 2, and lambda 3, so this will be along like this. So this is lambda 1, this is lambda 3, and this is lambda 2. So strain ellipse is like this, right? And we are observing the maximum direction and the minimum possible maximum direction, and a section with maximum deformation and a section with zero deformation. So a section with zero deformation eventually remain as circular, but the section with maximum deformation will turn into a linear feature. So that's why option B will be correct, so that we will see circular along yz section and linear along xz section. Okay. So if you have any doubt, you can ask, or we can go on to the next question.
ठीक है सर, आप मूव कीजिए, वो मैं एक्सेस ही गलत
No, you can say what you are talking about.
नहीं ठीक है सर, एक्सेस गलत दिया था मैंने, y की जगह x की जगह y दिया था, उल्टा बोला.
Okay, no problem. But keep in mind that whenever you are whenever you are dealing with lineation, right? Linear features, and if any question there is associated with lineation, always remember that it will be the strain ellipse, not the stress ellipse. For foliation, you can think about stress ellipse, because the development of foliation is directly related to the stress. But for lineation, it will always be the strain ellipse, because the minerals or the mineral grains or any feature, any strain marker that is deforming and producing the lineation will automatically align itself with the maximum, parallel with the maximum strain, maximum elongation, right? That is lambda 1. So principal stretching axis, lambda 1.
lambda 1.
Yes. So if you are dealing with if you're dealing with foliations, you keep in mind the stress ellipsoid. In that case, you will think of sigma 1, sigma 2, and sigma 3. But whenever you're dealing with lineations, keep in mind strain ellipse. That means you have to keep, you have to think of lambda 1, lambda 2, and lambda 3. So I may write it down. So foliation, stress ellipse, lineation, strain ellipse, and lambda 1, lambda 2. Okay. So the next question is, which of the following interfaces is likely to be considered as a secondary foliation? Option A, the interface between an underlying granite gneiss and the sandstone unit river bed. Option B, the interface between a shell sandstone layered sequence and the dike cutting across the unit. Option C, the interface between a formation where grain size starts to change. And option D, the interface between the host rock and a quartz vein intruding along a fault plane. So, which of the four options is likely to be a secondary foliation?
So it is interface between the host rock and the quartz vein, including along a fault.
Exactly. Option D is correct. Now, can you say what kind of interface is option A?
This is
The interface.
unconformity. Unconformity.
Exactly. So option A is an unconformity where we have a igneous unit and which has been overlain by a sandstone, or that is sedimentary unit that is deleting. That is denoting existence of an unconformity. Now, why option D is correct? Because fault plane is a fracture plane, right? And since it is a fracture plane, that means it has, if it is a shear fracture, considering a shear fracture, fracture plane is a shear plane. It is a plane where maximum shear has localized, and it is associated with deformation, right? So quartz vein that intrudes or injects or intrudes along the fault plane will produce the slickened sides, which is of secondary origin. Can you say what is option B? Sorry, option C, the interface between a formation where the grain size starts to change.
In myelites, where interface is there, the grain size reduces.
So, if I consider it to be simply a sedimentary origin, so
Uh,
myelinization is an option. Yes, it can happen when we are observing in a shear zone. So that can be the shear interface. Um, but if so, if I but that is more gradual because you cannot actually define any single plane in that case, right? Because the grain size reduction happens gradually from the host rock to the shear zone, and that transition is not sharp. If the transition is sharp, then definitely we can say that okay, so this is a plane of shear localization, and it can also be identified as a secondary foliation. However, that doesn't occur generally. The grain size reduction occurs very gradually, and therefore we cannot particularly draw any boundary in case of that. But if we talk in terms of sedimentary unit or sedimentary rocks, then the transition from one grain size to another will simply mean that we have two different rock units. Even within a sandstone, say we have a sandstone unit and one is coarse sandstone and is fine grain sandstone. So the boundary along which the grain size transition is actually happening, that is basically a bedding plane because you are differentiating between two deposits, right? So grain size reduction, I mean change in grain size. So if it was initially coarse grain and then it's transitioning to a fine grain, that means the energy of the deposition is changing. That means the deposition environment is altogether changing, and we are depositing a new phase of sediments. So that means it is obviously a new bed within a formation, right? And altogether, it can also be because of new
Rhythmic,
lithology.
it can be due to rhythmic deposition, transition,
Yeah,
regression. Yes.
exactly, translation, regression, these kind of things. So rhythmic deposition can also occur. So altogether, it will eventually lead to separate bedding planes, right? It will not be a single bedding plane or single strata. It will be different strata. So in terms of sedimentary origin, the transition of grain size along a particular interface defines a defines two separate strata. That means bedding plane. Okay, so let us move on to the next question. So, which of the following secondary foliations is not a penetrative feature? Option A, crenulation cleavage. Option B,
Slicken
nisocity.
slide, slicken slide.
Exactly. Option D is correct. Slicken sides. Slicken sides are associated with fault surfaces, right?
Due to movement of salt rocks.
Exactly. Slicken sides are associated with fault surfaces due to relative displacement of fault blocks, and this is generally we say that slicken sides are non-penetrative features, but it can also happen that the fault is occurring in a brittle ductile regime. That means any kind of brittle deformation associated with the rock will definitely be hampering the ductile deformation of the rock as well. So that is why if you observe any fault in a brittle ductile regime, especially phyllosilicate rich faults, so you will see that even though you have a very definitive fault plane, if you go in beyond that fault plane and break some part, you will also find some existence of very feeble silicon lines on the surface as well. So that is because the displacement that is taking place, it is affecting the, I mean, it is since the displacement is taking place in a viscous mode, not just in solid rock. It is occurring in some semi-solid rock which is undergoing brittle deformation. So the drag because of the fault movement is also affecting the rock inside the volume of the rock as well, and some very weak silicon lines can also occur in the volume of the rock. So that is a very special case, but in general, when we talk about fault movements on the upper crust of the earth, that is essentially strictly restricted to brittle deformation, and that is why whenever we see silicon sites on the exposed fault surfaces, we see that it is non-penetrative in nature. Okay, so moving on to the next question. Which of the following is not an indicator of fault? Mylonite, gauge, brachia, and conglomerate.
Conglomerate.
Are you sure?
Yes, sir. Conglomerate is a sedimentary deposit.
Yes, but the thing is, conglomerates. So if you have a brachiated zone or a gauge, fault gauge, so you can have a fault gauge material between the two blocks of the fault, like this way, and you can also have brachiated clasts within the rock, within the fault gauge material. So these clasts, they often come from conglomerate units associated with the wall rock, or else formation of this brachia and the gauge zone altogether with clasts in it, they can produce a conglomerate type rock. So this kind of conglomerate is not associated with depositional regime, but it can occur because of deformation of the unit. With deformation, I mean related to faulting.
Yeah, that is the clasts are mostly angular. In this case, mostly clasts are angular, uh,
Yes.
and the normal conglomerates we have mostly clasts are circular or
Circular, exactly.
depending
But
upon the transport medium and energy.
but if you see most of the um, exposures, especially in Himalaya, so you will find gauge, brachia, and conglomerate all associated all together. So in Himalayan faults, you will find mostly brachiated fault gauges, and you will also find conglomerate, which are associated with the fault gauge.
Sir,
I mean
in
the
Himalaya,
clasts. Hmm.
pardon. In Himalaya, it is a active. Presently, it is active. So older
Yes,
conglomerates have also contributed as a whole. As a whole, they have put in the gauge is the graben portion.
yes.
I've just working in North Delhi fault belt. North Delhi fault belt.
Okay.
So in that, after Rilos, when Alvar group has deposited, there's a
Hmm.
constant half graben structure in which a huge massive conglomerate has been deposited due to some
Hmm.
alluvial fans or some
Exactly.
mostly I think mostly conglomerates are in sedimentary origin. I have less uh, knowledge of structural geology. That's why I'm taking this program.
Okay. Okay. So you're
No,
doing research.
no, I'm presently scientific officer in DAE.
Okay, okay, okay,
Your Santanu sir's student is doing MTech under me.
okay.
I'm well aware of many of your, as Amar Agrawal is close contact
Yeah, yeah,
with
yeah,
me.
yeah,
Number
yeah,
of, I've just to refresh myself. I have done
yeah,
my
yeah, yeah.
MS.
That is very good. That is very good.
I just told
I'm
you.
very much, yeah.
So,
So
sir,
I think that this kind of this brachia and conglomerate, they are often found in I mean they are juxtaposed together. So presence of a fault, such as for example, if I see there is an unconformity, so we often associate the unconformity with the existence of a conglomerate, right? So that in that case, so why do we do that? Because if we talk about an unconformity, it will essentially indicate a hiatus in sedimentary deposition, right? So there is no deformation for a very long period of time followed by successive erosion. And in that case, whenever new deposition and depositional environment is created, the energy condition remains very high, and that is why conglomerate kind of rocks are being deposited. So depositing conglomerate will require very high energy environment, and also because of the uh, see brachia and clasts that we observe in a fault gauge. So those clasts are very big. So if I say that I have a fault gauge with very large size of clasts in it, that will indicate that the fault, I mean, the displacement, relative displacement of the fault is pretty less, because if you have very high displacement, only then you can produce high comminution within the grain and the grain size reduction can take place. But if I restrict the displacement to very few millimeters or centimeters, or even some few meters, in that case, the combination of the grains will not be high enough to produce the very fine grain gauge material. So gauge is often, I mean, not present in some fault planes, because producing gauge will require very high degree of combination. That means the grain size reduction has to go in the level of clay and silt, like that, and also you have to have very high uh, concentration of um, phyllosilicates within the rock. Only then you can produce the gauge. But if you have a conglomerate associated with the fault, you can easily extract clasts from that conglomerate that will act as the brachiated grain and brachiated clasts. So they will be angular and fragmented. So conglomerate can be associated with the existence of a fault gauge. I mean, crustal fault. But myelinite is strictly a brittle. I mean, myelinite does not associate with the brittle deformation. Myelinite is a signature of ductile deformation, right? Myelinite is only strictly restricted to ductile shear zones. So ductile shear zone means that there is no visible fault planes running through them. That means we are restricted to ductile deformation only. No loss of cohesion is taking place. But if I say brittle faults, that means the cohesion is lost, and therefore brachiated clasts, gauge material, associated conglomerate can, I mean, take place. Say for example, if I have a fault, how much likely is that? So if you are working on the North Delhi fault bed, so how much likely is that you can find myelinite in the fault gauge? It is quite not possible, I think, because myelinite is a very high temperature, high grade rock with very fine grain size. But for large crustal faults, you can find conglomerates and brachiated clasts. But how often do you encounter ductile signatures like myelinite in brittle fault. So
In Northerly, malonites are not there.
yes, exactly. So myelonites are
In Sonbhadra, I have seen the malonite.
myelonites are the signatures of the existence of ductile shear zones. So ductile shear zone will only be, I mean, myelinite will only be there if there is a ductile shear zone. So in no way we cannot associate any of the following three options with brittle ductile deformation. So these are obviously not present in ductile deformation. Only myelinite is a signature of ductile deformation, and that is why option A is correct in this case. Okay. So, sixth question says the mineral lineation can be determined from one, silicon fibers, two, overgrowths, three, mullions, and four, rods. The options are 2 and 3, B 1 and 4, C 1 to 3, and D 1 to 4. The silicon fibers is, of course, this is defining the silicon lines, right?
This will be 1 and 4.
Exactly,
Million.
1 and 4. Yes. So, overgrowth structure, it is not associated with mineral lineation. It is associated with overgrowth of mineral grains, orthogenic mineral grains, and maybe some reaction between grains that can show overgrowth. I mean, in the bound and the grain boundary is growing. That kind of structure is not associated with mineral lineation. So, if I talk about, so first of all, mineral lineation, the formation of mineral lineation. So, how silicon lines can help? Silicon lines are grooves on the fault plane. And often what happen, quartz veins intrudes along the fault plane, and the silicon lines provides space for mineral precipitation. So this feature is very frequently observed in the field. Wherever you see silicon lines and silicon side fault surfaces, you will see that there are stripes of quartz veins material. Quartz materials are precipitated along the, I mean, parallel to the silicon lines. So that is telling us that after the activation of the fault, the silicon lines are produced as grooves on the fault planes. These are scratches on the fault planes, right? And then the quartz vein intrudes through the fault plane because it is a fractured plane, so it is a weak plane, and easily the hydrothermal fluid can intrude. And after the injection of this hydrothermal fluid, the minerals will precipitate along the depressed area that are formed because of this silicon lines. So these grooves that are being created, they actually act as the space where the minerals can actually deposit. So that's how you will find some quartz pods and quartz veins, small veins, they're running parallel to the silicon lines on the fault surface. And these silicon lines, and because of this, their non-penetrative nature, these quartz veins are only restricted to the fault plane itself. So I went to Malanjkhand copper mines for doing my industrial research, and I have seen there that the most of the coppers that they extract from the quartz veins, they are along the fault planes, right? And those uh, those silicon lines, they are very scale dependent, right? Because if you have very large asperity faults, you will end up producing of silicon lines at least 10 to 15 centimeter thick, and they can go for up to several meters in length. Whereas silicon lines can also take place in millimeter scale or even micron scale as well. So depending on the fault, the aspect ratio and the size of the asperities of the fault surfaces, they can vary in different sizes and length. So I've seen that there, those quartz veins, they run parallel to the silicon lines, and they have pretty good amount of chalcopyrite and other deposits in it. So of course these silicon lines, their non-penetrative nature have helped us in terms of their economic viability, because then we know that okay, so having a fault plane narrows down the existence of this existence of this kind of minerals, like copper deposits and gold deposits. So you can easily find these minerals from them. So there is a very good economic value of these silicon lines, and because of their non-penetrative nature, it helps as well, right? So that is how silicon lines can be helpful for developing mineral lineations. Now, overgrowth structure, as I told, that they are not associated with mineral lineation, and they are mostly isotropic in nature. That means the overgrowth that is taking place, that is not anisotropic. Mineral lineation is direction oriented, so there is an anisotropy in that. But overgrowth is not anisotropic; it is isotropic in nature. Now, talking about mullions, mullions do not produce uh, mineral lineations. In fact, mullion is only taking place because of the competency contrast between different layers. So, for example, I have a high competent layer. So this is high competency, and the above layer, this is low competency. And because of the folding of this layer, I will eventually find the traces of this high competence layer on the low competence layer, and they will produce a trace lineation. So this is a kind of intersection lineation. Only because the so when do we observe the mullions? Only when the overlying low competence layer is being eroded, then only we can find exposed mullions. So these are like little hinges of the rocks, fold hinges. So these are high competent material that they are being folded. So these are not associated with mineral lineation, because they are not helping in depositing any kind of mineral deposits through any kind of intrusion or any secondary growth. So this is just an intersection lineation. It's a kind of intersection lineation. But roddings or rods, they are associated with mineral concentration along the hinge line of a fold. So if I have a very high, steeply plunging or steeply dipping fold, very tight hinge, then I may often encounter that monomineralic aggregates are taking place on the hinge line. So rods are essentially this kind of lineation which are defined by some mineral. It can be quartz, it can be calcite, pyrophyllite. These are kind of minerals. They occur as roddings. You will not find any kind of soft minerals like phyllosilicate or phyllosilicate kind of minerals or tourmalines. Yeah, tourmaline can be a pretty good candidate for roddings, even for even amphibole. But any soft mineral like talc, gypsum, or phyllosilicates, you will not find these minerals as roddings because they are soft minerals. Roddings will only occur if a very high competent material is being folded and it occurs as a tight hinge fold, and then only you can develop monomineralic lineations on the hinge, and that will be the rodding. And that is why you need harder material like calcite, you need quartz, apophyllite, or tourmaline. This kind of material can form in the roddings. Okay, so moving on to the next question. What kind of deformation mechanism may operate to produce syntaxial pressure shadow lineation? Option A, dislocation glide. Option B, Navarro herring creep. Option C, cobble creep. And option D, dissolution precipitation creep.
It will be, sir. I think it's D, dislocation, dissolution precipitation.
Exactly, dissolution precipitation creep. Because if you think about the process, so you have a clast, a rigid clast, which is not deforming. Remember, whenever we're talking about the formation of pressure shadow lineation, we talk about the deformation of the fringe, rotation and deformation of the fringe, and that is how the geometric characterization of the pressure shadow lineation is being done. So the clast is a rigid body that will not deform. So what is happening is that whenever the stress is being applied, so the stress concentration itself along the boundary of the clast will change. So at this point and at this point, you will have the maximum stress concentration. So if I draw the stress contour, so this will be like this. With the highest strain at the very beginning, and gradually the stress is decreasing. So this is how the stress contour will look like. And the stress expands it decreases in this hemispherical manner. So these zones, they become the low pressure zone. These are the high pressure zone. So since the stress is high at this point, the trace elements responsible for diffusion, they will become mobile because of the high stress acting on that point. They will gain sufficient activation enthalpy and they will become mobile. They will move. And where will they move? So the stress will drive the concentration. So from this point where the concentration is high, they will move towards the low concentration zone. And what will happen? From high stress to low stress region, if they are moving from high stress region to a low stress region, high stress region will make them metastable by providing high energy to the system, and they will become mobile. And because of their mobility and in the presence of a fluid, they will flow to the low pressure zone where they will again come into the equilibrium and they will settle down. So that is how the dissolution precipitation creep mechanism occurs. And because of the dissolution precipitation creep, the elements from the high stress region or high strain cap, this region is called high strain cap, they will eventually move towards low strain cap or low pressure zone and they will precipitate here. And this is how the now syntaxial pressure shadow means the fabric,
Same fabric and
yeah, the fabric and the clast will have the same composition. So that means the fabric that is being developed during the pressure shadow, there the material is coming from the clast only, not the wall rock. You have, if you have antitaxial pressure shadow, in that case the fabric composition will be same with the wall rock. That means the material is coming from the wall rock and not the clast. But in this case, for syntaxial pressure shadow, the clast is dissolving the material because of this high strain cap, and it is being deposited in the low pressure zone, and eventually you are producing the tail. So syntaxial pressure shadow is formed through dissolution precipitation creep, where the dissolution of material take place at the high strain cap associated with the clast where maximum stress is applied. Maximum stress concentration occurs. And this is how the pressure shadow lineation is formed. Okay, next question. Which of the following statements regarding cleavage refraction is true? Option A, buckling instability can produce buckling instability can produce cleavage refraction. Option B, flexural slip alone cannot produce cleavage refraction. Option C, flattening plane of the local strain ellipsoid remains parallel to the bulk strain ellipsoid during cleavage refraction. And option D, cleavage refraction is a non-penetrative event. So which one of the following statement is true? Is an important component to produce cleavage refraction. That means if I have two layers, and if flexural slip is not occurring within the layers, then I cannot form the cleavage refraction. It is not possible. So flexural slip is mandatory. Flexural slip is a mechanism for generating folds. So you will learn in the geometry of folds and the mechanism of folding. So buckling instability means if I have a layer and I am applying layer parallel compression, and after a certain amount of shortening of the layer, it will buckle. That means it will produce this kind of fold. So where there is buckling is involved, we will not be seeing cleavage refraction. So cleavage refraction essentially requires flexural slip. So this option is not correct. Right? So buckling instability cannot produce cleavage refraction. Okay. Now option B, flexural slip alone cannot produce cleavage refraction. Even though flexural slip is an important component to produce the cleavage refraction, it is not the only component because cleavage refraction fundamentally requires viscosity contrast between the layers. If there is no viscosity contrast or the competency contrast, then the cleavages will remain parallel. So if you have two different layers, and if they both have the same viscosity, effective viscosity, then what will happen is that there will be no competency contrast between the layers. And that is how, even if you produce the folds during through flexural slip, you will end up having parallel cleavage planes, right? So along with flexural slip, one also requires uh, viscosity contrast between the adjacent layers to produce cleavage refraction. So option B is correct because flattening plane of the local strain ellipsoid, actually during the cleavage refraction, the flattening strain ellipsoid, the flattening plane of the local strain ellipsoid rotates along the direction of refraction. And does not remain parallel with the bulk strain ellipsoid. So that is how option C is also wrong because it is eventually rotating. And cleavage refraction is of course a penetrative event because the refraction is taking, because the folding, it is associated with folding, and folding is a penetrative event, right? You cannot see fold in particular plane or layer and then again it is disappearing. That cannot happen because cleavage, because of the cleavage refraction phenomena, it is associated with folding. Therefore, since folding is eventually a penetrative event, cleavage refraction also has to be penetrative in nature. So option D is also wrong. Option B is correct because flexural slip alone cannot produce cleavage refraction, and you also require the most primary component, that is the viscosity contrast between the adjacent layers. But you also require flexural slip because without the flexural slip you will not produce the axial planes. So axial planar cleavage or axial planar foliation is required to produce the cleavage refraction, and flexural slip is the only mechanism through which you can produce both. And you also need the viscosity contrast, and that is how you can end up producing cleavage refraction. Okay, so moving on to the next question. Cleavage is observed to be entering from a low competent layer to a high competent layer during colding. Which of the following options regarding cleavage refraction is likely to occur in this situation? Option A, cleavages will converge towards the trace of the axial plane in the incompetent layer. Option B, cleavages will diverge away from the trace of the axial plane in the competent layer. Option C, cleavages will diverge away from the trace of the axial plane in the incompetent layer. And option D, cleavages will converge towards the trace of the axial plane in the competent
Sir, C is right. In competent layer, divergence is there.
layer. So this is your competent layer. Say for example, and this is your incompetent layer. And this is the trace of the axial plane hinge line. Now we have some cleavages, axial planar cleavages that are entering into the, say for example, this is entering into the competent layer. From incompetent layer, it is entering into the competent layer. So in this case, from the perspective of the incompetent layer, it will diverge away from the axial plane.
Yes, sir.
And then again, if we have another incompetent layer, it will again converge like this. Right? So in this case, cleavages will diverge away from the axial plane in the competent layer. So option B will be correct because since it is entering from the incompetent layer to the competent layer, we have to see what is happening in the competent layer only. So in the competent layer, as the cleavages are entering from the incompetent to competent layer, because of the strength, it will simply diverge. So it is very similar to optical refraction. So you have glass and light is entering at an angle to the interface of glass and air. So if this is air, so just like that, if you have low refractive index material and light is entering from low refractive index material to high refractive index material, it will bend towards the principal axis, right? And if the light beam is entering low refractive index material from high refractive index material, it will diverge from the principal axis, this one. So similarly, since it is going from incompetent to competent, so incompetent means it is soft and competent means it's hard. So the track will easily be diverted and it will go away from the axial plane. So entering from incompetent to competent, it will show divergence with diverging away from the axial plane. So entering from incompetent to competent layer. In this case, diverging away from axial plane and entering from competent to incompetent. This will produce converging towards axial plane. So this is how through cleavage refraction you can also identify which one is competent layer and which one is incompetent layer. Okay. Question number 10. The mineral lineation observed lying on the axial planar cleavage of a regional fold in a ductile shear zone will likely to plot on the dash domain of a 3D flint diagram. Option A, constrictional domain. Option B, plane strain domain. Option C, flattening domain. And option D, either constrictional or flattening domain. So if you remember the flint diagram, we have k is equal to 1, k is equal to 0, k is equal to infinity, and we have constriction. This is plane strain. This is flattening. So which option do you think will be the correct answer?
Will be C, flattening domain.
Exactly. It will be C. Because when we are talking about ductile shear zone, folds are generally forming in asymmetric manner. Right. The asymmetric folding means compression and shear is compression, simultaneous compression and simultaneous shearing is producing the deformed folds in a ductile shear zone. So what is happening is that the axial planar cleavages that are being formed like this, so they are the result of continuous flattening of the material on the um, axial plane, right? So if this is your initial folding with some weakly developed foliation, if you further flatten out this fold, this will produce this shear zone with extremely tight folds, and all the mineral grains, the platy minerals, they are aligned on the, they are perfectly residing over the axial plane. And this is a perfect example of flattening type of deformation. And that is why in Flynn diagram, you will see that all the lineations are plotting on the flattening domain. Okay, so moving on to the next question. Rock A and rock B both shows compositional bending and no macroscopic signatures of deformation on a hand specimen scale. How would you determine the existence of a secondary foliation from these rocks? Option A, only by studying the mineral assemblage. Option B, only by studying the shape of the mineral grains in thin section. Option C, by studying the mineral assemblage and observing the microstructure in thin section. And option D, only by observing the microstructures in thin section.
It will be C, by studying the mineral assemblage and observing the microstructure.
Exactly. Because both of the rocks are showing compositional bandings, but no discernible signature on the hand specimen scale. That means one of the rock is nice and the other maybe sedimentary rock. It can happen like that because nicosity on a hand specimen scale you will not find any preferred orientation of minerals or any kind of foliation planes on the gneissic rock. Of course, if you have an idea of the mineral assemblage of a gneiss, you can directly identify it through your hand specimen scale. But it, if say for example, in terms of a layman who is not expert in identifying the minerals from hand specimen scale, they have to look for other signatures. Right? That is, what is the exact mineral assemblage in thin section scale? And if you observe the thin section, you will find whether the assemblage is a metamorphic assemblage or it is a sedimentary assemblage. So mineral assemblage is important because we can identify whether the assemblage is metamorphic or sedimentary or igneous. And microstructure will provide information on cleavage microlithon domain. And that is how, and there will be some orientation of minerals. So you can also find shape preferred orientation of mineral grains. This is known as SPO. Shape preferred orientation of a key mineral, say for example, it can either be quartz or it can be, if it is a very high grade rock, there can be amphibole. These kind of minerals they can show. Even there can be existence of biotite. So these kind of minerals they can pretty easily develop the foliation, and they will show the traces of the foliation, and you will see specific cleavage and microlithon domain. And of course, if the rock is overall deformed, you will find the shape preferred orientation, that is the elongated grains. They are elongated and oriented in a particular direction. And if you find the shape preferred orientation SPO of mineral grains, then you can identify the trend of the deformation, whether how the foliation planes are oriented in the sample. Okay, question number 12. A rock does not present any discernible cleavage domains in hand specimen. However, microstructure presents an irregular microlithon domain with braided cleavages in the thin section. How will you classify this secondary foliation? Option A, discretely crenulated spaced foliation. Option B, zonally crenulated spaced foliation. Option C, stylolytic disjunctive spaced foliation. Option D, microdisjunctive continuous foliation.
I think it's D, micro-destructive continuum.
Exactly. Because in hand specimen scale, if there is no discernible cleavage domains in hand specimen scale, that means it is not spaced, it is continuous cleavage, right? Because spaced cleavage has at least few millimeters of spacing, at least in the order of 10 to greater equal to 10 millimeters of gap. That means the microlithon domain, it has to be in the order of millimeters to centimeters. That is how you will be identifying whether the foliation is spaced or continuous. So no discernible foliation plane that are observed on the hand specimen scale means the foliation is not spaced. And obviously the option D will be correct because it is the only option for continuous foliation. So in this case, option D is the right answer. Okay. Question number 13. We have only one question left. So find the direction of the hinge of the regional antiform. Option A, towards the opening of theta. B, option towards the opening of 90 degree minus theta. Option C, towards the opening of alpha. And D, towards the opening of 90 degree minus alpha. This is a second order fold. This is a second order fold, and this is the axial plane. So you should know that this fold is a Z fold, right? This is your primary bedding plane. This is your trace of axial plane, and this is again your primary bedding plane. So this is a Z fold. And from the orientation of axial plane, you can identify in which direction the hinge should lie. Since we are talking about antiform, that means the Z fold will always be on the left limb of the antiform. Z fold always forms on the left limb of an antiform. Okay. So if this is an antiform, you will find Z fold in this limb and S fold in right limb. So this is left limb and this is right limb. So antiform will have Z fold in the left limb. And from the axial plane, even if you cannot find the second order folds, you can also determine the hinge of the fold, regional fold, the direction at which you can find the hinge of the regional fold from the axial plane itself. This is called the vergence. Vergence says that the acute angle, sorry, acute angle between cleavage bedding intersection actually this will be the opening of the acute angle. I may write it properly because it will not make any sense. The opening of the acute angle between the cleavage bedding intersection will be the direction of the hinge line. So this is called the vergence of asymmetric folds, and from that you can determine where, in which direction the hinge is lying. So in this case, in which direction the acute angles are opening between the cleavage bedding intersection?
Alpha.
Exactly. So this is the opening. So this direction, this and this direction is the direction of hinge. So towards the opening of alpha will be the direction where you can find the hinge of the regional antiform. So this is how your foliation plane, stresses of foliation plane and the intersection between bedding plane and axial plane or secondary cleavage, you can identify the disposition of the regional fold, the hinge, the limb, and eventually their orientation, their mutual geometry from just by studying a single exposure. So that is how helpful these kind of features are. Okay. The last question is, which of the following is a primary lineation? Hornfels, Schlieren, stylolite, and Rottings.
On
Yeah, Hornfels and Schlieren, they are both correct options in this case. Stylolites are, of course, disjunctive cleavage, and Roddings is mineral lineation. But Hornfels, it is basically a metamorphic texture associated with contact metamorphism, where needle-like mineral grains are formed due to reaction, and they may sometimes present as lineation. But this is strictly not associated with deformation, and that is why it is primary. Similarly, Schlieren, this is a primary igneous texture associated with plutonic igneous rocks in which alternate dark and light colored mineral segregation is observed. Okay, so these were the two question, all the questions regarding
Sir,
foliation and lineation. Yes,
if you put some light on cleavage transaction.
cleavage transaction is basically the uh, it is a form of intersection lineation, correct? Cleavage transaction means the concept that I just already told you about the vergence, right? So in an asymmetric fold, the cleavage planes they transect with the bedding planes in such orientation that it produces an angle and it rotates with uh, further deformation. So, say for example, you have an axial planar cleavage, and at the hinge line it should be perpendicular. But now you are producing asymmetric folds. So what will happen? These axial planes will start rotating because the entire fold structure is rotating because it is producing asymmetric folds. And this rotation of these axial planar cleavages is also associated with the rotation of the hinge of the fold. And this is the concept of vergence and cleavage transit.
For example, if strata is folded is F1 and some
Yes.
axial cleavage is there, and again
Hmm.
it is refolded in F2, then cleavage transaction will take place.
Mm, that will depend on
If both are F1, F2 are coaxial.
uh, sorry again I just couldn't understand your question.
Uh, if they
Hmm.
are F1,
Hmm.
F2, F3, three types of fold is there.
Hmm.
F1,
Hmm.
I'm just asking about F1 and F2. If
Hmm.
bed is folded in F1,
Hmm.
there will be some axial plane cleavages is there,
Hmm. Hmm.
and
Hmm. Hmm.
this fold is again coaxially folded in F2. Then what
Okay,
will
okay. So say for example, so I have a fold like this. And I have an axial plane. Okay, so this is my fold axis F1, and this is my axial plane AP1, right? And this is the bedding plane S0. Now I am refolding this fold coaxially. Coaxial superposition, if I talk about, I can fold it this way.
Yes, yes, yes. Hook type, hook type. Yes.
Hook type, yes. So this is this layer which is refolded. This is your S0. This layer, this is your refolded S1, and this will be your new axial plane. So coaxial deformation, it will generally mean the new axial plane and the old axial plane, they are parallel to each other. So if you see, coaxial
Right.
deformation will produce parallel axial planes, but cleavage transect is non-coaxial. That means these two cleavages will not be parallel in that case. So if you have non-coaxial superposition, if you say you have type 2 deformation, that is non-coaxial,
Yes, yes.
and in that case, your cleavage will not be parallel. Cleavage transect means that you are rotating because of your producing asymmetric folds. You are rotating the cleavages with respect to each other so that it will not be parallel. In this case, the S2 and S1, they're parallel. Cleavage transect means you are producing cleavages in such a way that they will not remain parallel. And that is only because you are producing asymmetric deformation. If you have produced asymmetric folds tend to be non-coaxial. So if you have non-coaxial deformation, then only the cleavage planes will not remain parallel, and the angularity between cleavage planes, successive cleavage plane, is the concept of cleavage transect. Transect means it is trans, matlab, these are
At an
intersecting with
angle.
each other at an angle. They're transecting. Transecting means they're at an angle. They are not parallel. So it is essentially related to non-coaxial deformation. Okay.
Okay, thank you.
Okay. Thank you very much. So I am ending today's discussion session, and in the next live session, we will be talking about.
Happy belated Teachers Day.
Oh, thank you, and same to you. Same to
Okay,
you. Thank you,
thank
sir.
okay, thank
Okay.
you. Thank you.